Hope all of you are doing good. Let's take up topic diffusion. All right, there we go. We have 40 plus students. Wait, 41. Okay. All right, now diffusion, guys. Previous lecture, I had a discussion with all of you about the definition of diffusion, and there are two types of law, which is fixed first law and also fixed second law, which governs steady state and non-steady state diffusion. For steady state, it is independent of time. For non-steady state, time dependent. Right. So for today's class, I'll be focusing on non-steady state diffusion and factors that influence diffusion. Also, I'll be giving you one example for as a roundup for today's lecture. Okay, after the class I'll be having tutorial which I'll be discussing on the exercises involving lecture 1 and lecture 2. So that will sum up our whole lecture 1 and lecture 2, and we will be continuing with lecture 3 next week. Okay, let's go step by step. All right, before we begin, just a quick recap of previous lecture. All right, this diffusion. All right, diffusion essentially mean a transfer of mass, okay, a transfer of solid within the atom arrangement by itself. That's the definition. If you look at here, okay, diffusion means phenomenon of material mass transport by atomic motion. So your atom is transferring from one point to another point. Why does this happen? This happens because you have an extra energy given to the atom to reach its activation energy and unlock itself from the governing energy within their atomic arrangement. So once it has the extra energy to loosen itself, it starts to transport. Diffusion resulting in a more stable atomic arrangement. Usually we call that as heat treatment. Okay, usually material engineers call them as heat treatment, diffusing, right? So where we were, okay, now atomic movement within the atomic structure arrangement with vary with temperature and kinetic energy, and we call that as phenomenon of heat treatment. All right, you can look at this figure over here, depicts the ideology behind diffusion. And if you could recall about the example that I told you, mosquito bite in a room. So that is how diffusion works. Initially, you have a concentration of copper here and you have a concentration of nickel here. After some time, both mixes together in a randomly arranged manner. Okay, you can't predict diffusion. It depends on the energy level for each individual atom. So you try to imagine the complexity of energy for each atoms. So you can't model this, you can't predict this. Okay, we just know that the concentration before diffusion and the concentration after diffusion changes. That is the basics of Fick's law. So that is the reason why all the formulas associated with lecture 2 having concentration profile, okay, which I have discussed this previously. Teo Chian Wang pressed wrong. Okay. All right. Shall we continue? Okay. Guys, you can view my screen, right? Okay. All right. All right. Because I'm getting a lot of Windows pop-up. I don't know what is that. Okay. All right, okay. Okay, now we have two types of diffusion. The first one is self-diffusing, and the second one is impurity diffusion, interdiffusion. Okay, these are the basic figures. And two mechanism involve diffusion, which is vacancy diffusion and interstitial diffusion. Vacancy diffusion can be associated with self-diffusion. Interstitial diffusion can be associated with impurity diffusion, right? Interstitial atom, vacancy, the atom itself move, all right? And also I've given you the introduction for diffusion flux, which is J is equivalent to mass over cross-sectional area times the diffusion time. That is diffusion flux, right? So in steady state diffusion, we have two types of what they call governing process for diffusion, which is steady state and non-steady state. Okay, steady state, for the first fixed law, it discusses about the steady state diffusion, and it says that diffusion flux does not change with time, okay, independent of time, and it is proportional to the concentration gradient, and this is the concentration gradient. As I mentioned to you earlier in this lesson, concentration plays an important role in diffusion, okay, in this, right? So I'm just recapping, guys. I just recapping, try to heat up for today's lesson, then we can start with our lesson, right? Okay, all right, concentration gradient, steady state diffusion, this is the formula. D is your diffusion coefficient. You have your diffusion flux, and this is your concentration gradient, rate of change of concentration, del C, over rate of change of distance from the surface to an unknown distance. For example, semi-infinite solids. Okay. All right, non-steady state diffusion, our today's lesson. Now, for non-steady state diffusion, the diffusion flux and the concentration gradient at some particular point in a solid varies with time. Highlight this. Vary with time. Okay, non-steady state diffusion. I don't know why I can't highlight all. Okay, good. With a net accumulation or depletion of the diffusing species resulting. So you have a net accumulation or depletion of diffusing species. Okay, it can be accumulate or it can be deplete. All right, depending on types of diffusion that you wanted to have. All right. Sometimes coating is accumulation. Depleting is heat treatment. All right. So this involves most practical diffusion situation. So most of the diffusion situation involves non-steady state because it varies with time. All right. If you look at this figure, whoa, right. Okay, if you look at this figure shows the concentration profile for non-steady state diffusion taken at T different time. T1, you have this concentration profile. At T2, you have another concentration profile, and at T3, you have another concentration profile. So these are independent of each other. Okay, so the time is varies. Whereas for steady state diffusion, the time is fixed. Okay, diffusion flux does not change in time. Diffusion flux. Okay. Now, for non-steady state diffusion, Fick's second law says that if the diffusion coefficient is independent of composition, okay, I'm repeating, if the diffusion coefficient D is independent of composition, okay, D is independent of the composition, the time rate of the change of concentration is proportional to the second derivative of concentration. There you go. The time rate of the change of concentration is proportional to the second derivative of concentration. And this is your diffusion flux. Sorry, diffusion coefficient. Okay, diffusion flux is J. Okay. See, diffusion coefficient is independent of the composition. Independent of the diffusion coefficient is independent of the composition. And the time rate of change of concentration is proportional to the second derivative of concentration. All right. Solution to this expression is possible for a semi-infinite solids. Okay, semi-infinite solids means your surface is CS surface and it goes towards a one plane, single plane to infinite. All right, in which none of the diffusing atom reaches the bar end during the time over which diffusion takes place. Okay, so this is your bar. None of the diffusion atom reach the bar end, so it is infinite. All right. So theoretically, they are trying to explain what is a semi-infinite solid. And for semi-infinite solid, the length, okay, this is the understanding. Length must be more than 10, and then square root of dt, where L is the length of the bar. Okay. To obtain the solution for the expression, the following assumptions are made. All right. So this is the expression given, and this is the assumptions that are made. Okay, now, before diffusion, any of the diffusing solute atoms in the solids are uniformly distributed with a concentration of C0. Highlight this. Before diffusion, any of the diffusing solute atom, okay, the solute atoms that are going to diffuse in the solids are uniformly distributed with concentration C0. C0, okay, all right, C0, okay, here, C0. The value of X at the surface is 0 and increase with the distance into the solid. Okay, the value of X at the surface is 0 and increase with the distance of solid. Okay, the value of X at the surface is 0. Okay, at time 0. The time taken to be 0 the instant before diffusion process begin. Okay, the time taken to be 0 the instant before diffusion process begins. So for this assumption, it can be figured out by the conditions over here. So for time is equals to 0, so this is the time, the first time at 0 before the diffusion begins, the concentration is C0. Okay, the concentration is C0. So the time taken, the time is 0 before it begins at the distance of 0 at the surface and infinite. Okay, infinite means it is semi-solid infinite. All right. As time ticks, diffusion takes place. The concentration starts from concentration at the surface. Imagine, guys, diffusion starts at the surface of an object, right? Of a material. Okay, don't talk about object, of a material. So when diffusion starts, the concentration you should take is the concentration at the surface of a material. So that is the constant surface concentration at X is equals to 0. Because it is surface, X is equal to 0. All right. And once the time rolls out, the concentration to be at C0, which is the concentration of solids at X is equals to infinite, unknown distance. Okay. Try to understand this, and then application of the boundary condition of the expression yields this. Okay, Cx, which is the concentration of unknown distance, minus C0, the concentration 0 initial concentration, divided by the surface concentration minus initial concentration. where Cx represent the concentration at depth x, unknown distance, after time t, once the time starts ticking, and ERF stands for Gaussian error function. Okay, so this is the concentration profile. At x0, that is your surface concentration, high concentration. All right, once the diffusion takes place at the surface and you are traveling after the surface, the concentration becomes C0. Okay, and this is your Cx, any distance between the surface and towards the end of your x, which is C0. Okay, so Cx minus Co, Cs minus Co. So Cx minus Co, which is this concentration gradient, and then for this curve, Cs minus Co, which is this. Okay, so this is the representation. Okay, this is the representation I've discussed to you over here. For t is equal to 0, before it starts, concentration is C0. At x is equal to 0, or x is between 0 or infinite. When the diffusion begins, so t starts, it can be above 0, and diffusion starts at the what they call that surface. So concentration at surface Cs at x is equal to 0. Okay, x is equal to 0. So diffusion takes place here until it travels further. It reaches the concentration of C0 at x is equals to infinite. All right, try to understand this. This is just a repetition of this. Okay. Okay, any questions until now? Non-steady state diffusion. So the formula that you should memorize is, where is it? This. Any questions so far, guys? All right, so you can understand, huh? Okay, good, thanks. All right, we shall continue. So that's about it. We have two types of diffusion, two process of diffusion under the fixed law, fixed first law and fixed second law. All right, fixed first law is steady state diffusion. Fixed second law is non-steady state diffusion. Please highlight or write it down in your notes. Okay. Oh. Okay, now guys. So previously I did mention to you about temperature being the government body, right? Temperature makes a huge difference in determining the activation energy of an atom. All right. Now, besides temperature, there are some what they call that factors also involving in the influence of diffusion, the rate of diffusion. Okay. There are few factors that I'm going to discuss with you. 1, 2, 3, 4, 5. Interstitial diffusion. No, we have 3. 1, 2, 3. Yeah, 3. All right, 4 actually, 4. Okay, let's go through one by one. All right. Okay, now the diffusing species as well as the material influence the diffusion rate. Okay, remember guys, remember about the vacancies and also interstitial at the early point of lecture. Where is it? Okay, vacancy diffusion and interstitial diffusion. I did mention to you that interstitial diffusion is greater than vacancy diffusion because interstitial diffusion has smaller size, so it can seep through the voids between two atoms. So one of the factors that affects diffusion besides temperature is the diffusing species as well as the host material influence the diffusion rate. Highlight this. As for example, the diffusion coefficient at 500 degrees Celsius, okay, fixed temperature, is greater in carbon alpha ion interdiffusion, which is this 2.4 times 10 to the power of -12 meters square per second, as compared to that of carbon self-diffusion, which is 3 times 10 to the power of -21 meter cube per second. This is due to the fact that the self-diffusion of alpha ion occurs by vacancy mechanism. So this is under vacancy mechanism, whereas carbon diffusion in iron is interstitial. Carbon diffusion in iron is interstitial. Okay. So take note of this. So interstitial and vacancy. All right. Now next factor is crystal structure of the host material influence the diffusion rate of interdiffusion. For example, between BCC and FCC, the diffusion coefficient at 900 degrees Celsius is greater in carbon alpha ion BCC interdiffusion, which is 1.7 times 10 to the power of -10, as compared to that of carbon gamma ion, which is FCC interdiffusion, which you have a value of 5.9 times 10 to the power of -12. Okay, this is due to the fact that between BCC and FCC, the interstitial diffusion occurs more rapidly in BCC crystal structure as compared to FCC crystal structure, since there are few interstitial spaces in crystal structure within a lower atomic packing factor. Okay. Now, if you have the reference book, you can get the tabulation of diffusion data. Okay. Usually behind the reference book, you have all the data. Okay, so for the sake of knowledge, you can have a look on the tabulation of diffusion data. So this kind of data will be helpful during your test and also during your final assessment. Okay, so you can see the diffusion rate stated over here. And this is the diffusing species. And this will be the host material. And this is the rate. Then you have the activation energy. Okay. And this is the calculated values. Right. Now, types of crystal imperfection. More open structure grain boundaries increases the diffusion. Highlight this as well. More open structure, if you have more grain boundaries, it increases the diffusion rate. Okay, highlight this. And the known one, increase in temperature would cause an increase in the diffusion coefficient and thus the diffusion rate. Increase in temperature would cause an increase in diffusion coefficient and thus the diffusion rate. Okay, for example, the self-diffusion of ferrum ion in alpha ferrum ion in the diffusion coefficient increased from 3 times 10 to the power of -21 to 1.8 times 10 to the power of -15 in a rising temperature from 500 degrees Celsius to 900 degrees Celsius. See, when you increase from 500 to 900, the diffusion coefficient increases from the value of -21 to a value of -15. That's a huge leap. So temperature is rule number one for you to increase the diffusion rate, as I mentioned to you last week. Okay, please take note of these as well. A large activation energy result in a small diffusion coefficient. So the activation energy must be lower so that the atom can reach activation energy faster. If you have very high activation energy, your diffusion coefficient is lower because atom needs to have huge amount of energy for it to overcome the energy governs the bonding between two different adjacent atoms. I like this as well. Okay, so we go to the next what they call that formula. We have diffusion coefficient D. D is equals to diffusion coefficient is equals to D naught, where D naught is a temperature independent pre-exponential diffusion coefficient D naught, and exponential QD is activation energy or energy required to produce the diffusive motion of 1 mole of atom. Definitely I'll be giving you this if you have an example. R and T is R is your gas constant and T is temperature in Kelvin, absolute temperature. Okay, just take note of this formula, right? Okay, just a quick small example of the application of diffusion. So one of the application of diffusion that I would like to discuss here is case hardening, where case hardening is a technique by which both surface hardness and fatigue life are enhanced for steel alloy. So that is case hardening. So case hardening can be achieved by diffusing carbon into iron. Here, case hardening can be accomplished by increasing the surface concentration of carbon via diffusing in a process termed carburizing. So I'm very sure you heard of carbon ions, right? The higher the concentration of carbon in an ion, the higher the strength of an ion, the higher the strength of the material. I'll be covering these, I don't know, maybe in week 5, 6, something like that. Okay, I'll be introducing types of iron, carbon content, and so on. Okay, so that is one of the example for diffusion, which is case hardening, carburizing. Okay, case hardening, carburizing. In carburizing, the steel piece is exposed to an elevated temperature to an atmosphere rich in hydrocarbon gas such as methane. The keyword here, guys, the keyword here is elevated temperature. So why they increase the temperature? It is to increase the activation energy for the diffusion material, diffusing species. Okay. In a hydrocarbon gas such as methane, CH4. So C will be unbound with H4, and this C carbon will start diffusing in ferrum, which is Fe, iron. Okay. So that's about it for lecture 2. Now let's look at the example. All right. Any questions so far? Any questions, guys, so far? Okay, all right. All right, let's look at an example. All right, now a plate of iron is exposed to a carburizing carbon-rich atmosphere on one side and a decarburizing carbon deficient in another side. Okay, hold on. Okay, at atmosphere on the other side at 700 degrees Celsius, so they have given you the temperature 700 degrees Celsius. If condition of a steady state is achieved, so steady state law, right? We are talking about Fick's first law. Calculate the diffusion flux, which is J, okay, of the carbon through the plate, okay, okay, so you have an iron plate and you are exposing that ion into a carbon-rich atmosphere at one side and carbon-deficient atmosphere at the other side. Now the question is, if the condition of steady state is achieved, calculate the diffusion flux of carbon through the plate if the concentration of carbon at position of 5 and 10 mm, okay, 5 and 10 mm, beneath the carburizing surface are 1.2 and 0.8 kilogram per meter cube. So this is the concentration at the position of 5, which is 1.2, and 10 mm, which is 0.8. Assume the diffusion coefficient of 3 times 10 to the power of negative 11 meter cube per second at this temperature. So this is the diffusion coefficient. They ask you to calculate, where is it? Calculate the diffusion flux. So this is the diffusion flux formula. J is equals to negative D. D is your diffusion coefficient. Concentration of A minus concentration of B. Distance of A minus distance of B. Okay, this formula is taken from your lecture. Where's your lecture? Is here. Yeah. Okay, so you have negative direction of diffusion. Okay, so this is your diffusion coefficient, all right, taken from here, given, and this is your so this is your concentration, 1.2 at the surface, CS, and 0.8, all right, beneath the carburizing, and the distance is 5 and 10 mm, 5 and 10 mm, okay, and change that into meter, then you have your diffusion flux. That's all. Okay, calculation for this subject is very straightforward. So there'll be formula and you just calculate it according to the given formula. Just that most of the students make mistakes on the units. Okay, units plays a vital role in engineering materials, where you have lots of units in mm, but you need to change that into meter and the temperature to Kelvin. So from my experience, students make mistakes in converting the units because calculation in this subject is straightforward. Okay, guys, any questions? Brothers, any questions, guys? Can you understand the lesson 3? We have 48 students. All right. Come on, if you have any question, please ask, because we are rounding up for today's lesson. So next week I'll be starting with lecture 3. No questions. Okay, I saw some other example use atom. I got disconnected halfway from this question. Okay. I saw some other example use atom over meter cube for concentration. Yes, you can convert those. You can convert those from concentration to weight percentage concentration as well. In fact, in tutorial, you have one question related to the example that you have mentioned. Yes. The unit must be always in kilogram per meter cube. Because if you look at the flux, Where is it? Yes. Yep. All right, guys. Yes. Lua Wen Zheng. Yes. Concentration must be in kilogram per meter cube. Okay, guys. Any other questions? You're clear, right? With my voice, any difficulties in hearing? Okay, all right. Okay, guys. Okay, if there's no questions, all right, now I'll stop the recording. If there's no questions, we'll be having tutorial later at 11:30.